Welcome back to LabRat Scientific. Now today I want to talk about how the wind affects the trajectory of a model rocket. Now it's a little difficult to see those effects using videos of actual rockets, so I'm going to have to use animations to get my points across. But don't worry, I've got some videos, I've got a demonstration that will help reinforce the concepts I'm going to talk about. First, let's take a look at a sounding rocket launch. Notice how the surface winds blow the rocket exhaust towards the left. Low-level and high-level winds are measured prior to a sounding rocket launch, and the launcher elevation and azimuth are adjusted appropriately to get the rocket to land in the desired impact area. Here are two NASA launch pictures. In the image at the left, notice the shape of the smoke trail. This shape is due to the winds near the surface. In the image on the right, notice the smoke trail is very straight. This means the surface winds were very calm at liftoff. Now let's take a look at how a thrusting rocket behaves in the wind. Here I have my rocket sitting on the launch pad. I'm going to depict the vertical velocity and horizontal velocity with blue and green arrows as the rocket flies. So here's the wind profile, and it's occurring between these two altitudes. I'm going to assume that the rocket is launched vertically initially. As the rocket begins to thrust upwards, you'll see that the velocity vector in the vertical direction grows, but since the rocket's flying straight up, it has no horizontal velocity. That continues until the rocket hits the wind layer. Now, as the wind pushes on the fins, it will cause the rocket to pitch into the wind. You'll see the rocket continues to accelerate upwards, but also begins accelerating in the horizontal direction due to the pitching rocket. Now, the rocket will continue to pitch more and more into the wind until it leaves the wind layer. At that point, it will assume its constant body attitude and accelerate upwards and downrange. However, recall, since the rocket's flying in a gravity field, it will fly a parabolic trajectory due to the gravity turn. Now let's take a closer look at the thrusting rocket as it enters the wind layer. Now here's my rocket, and I depict its velocity vector with the blue arrow. And here's the wind blowing on the side of the rocket. Now, since the velocity vector is already inclined to the wind, a small component of the wind will actually reduce the size of the velocity vector. Now, this doesn't mean the rocket's slowing down, it just means it's not accelerating quite as much. Now, let's take a look at just the airflow hitting the fins. And this airflow causes a moment about the center of gravity, which causes the rocket to pitch. As the rocket pitches more and more into the wind velocity reduces the velocity vector even further. You'll see that depicted in a slightly smaller arrow. Now, let's take a look at a simple demonstration to show how the wind causes the rocket to pitch. Now, let's do a simple demonstration using a model rocket that's on a pivoting axis and a simple box fan here to show how a model rocket will pitch into the wind. So, now the rocket is flying straight up, there's no wind. If I turn on the wind, you'll see that the rocket begins to pitch. And that's due to the aerodynamic forces acting on the fins, creating a moment around the center of gravity of the rocket, causing it to pitch into the wind. Now, a rocket with a large static margin or a large stability will tend to pitch more than a rocket with a smaller stability. Again, turn off the wind, and the rocket will tend to pitch straight up again. Now, you can sort of see this effect in this model rocket launch video. Notice how the rocket seems to pitch downrange, that's into the wind, and the wind blows the smoke back towards the camera. The end result is that the rocket will not fly as high, but will fly farther downrange. Now let's take a look at how a coasting rocket responds to a wind layer. First, we're going to look at a case where the rocket's flying vertically. Now here's my coasting rocket down here at the bottom. You'll notice that it already has a vertical velocity, and that was due to the thrusting phase of the rocket. Now, as a rocket ascends, the velocity vector isn't going to change much. In reality, it'll probably decrease due to gravity, but not a whole lot in this short time frame. Now, when the rocket enters the wind layer, you'll begin to see a horizontal velocity building up. Here it's relatively small, but as it flies in a layer longer, you'll see that the horizontal velocity increases. Now, since the rocket is not thrusting, it will not fly into the wind, but will begin to coast with the wind. You'll see that the velocity increases horizontally, and over time, the vertical velocity starts to decrease. Now, at some point, the coasting rocket will pick up a horizontal velocity that's equal to the wind velocity, and you'll see the vertical velocity is decreasing. And that's due to the increased angle of attack as the rocket pitches into the wind, giving it a higher angle of attack relative to the velocity vector. Now, as the rocket leaves the wind layer, it will begin to reorient itself with the original velocity vector, but still move in the direction that the wind was pushing it initially. Now let's take a closer look at the coasting rocket as it enters the wind layer. Here's my rocket, and its velocity vector is depicted by the blue arrow, and the velocity is going straight up. However, the wind blows on the side of the rocket, and that causes the velocity vector to shift to the left. So the rocket is now flying straight up, but the wind is also pushing it to the left. Now let's focus just on the wind blowing on the fins. It causes the rocket to pitch into the wind. However, since it's not thrusting, it's not flying to the right, it's actually drifting more to the left. And the velocity vector tilts slightly more to the left. And as it stays in the wind profile, it pitches more, and the velocity vector changes ever so slightly to the left. Now, at some point, the rocket picks up the same velocity as the wind, so the velocity vector will not shift much. Now let's take a look at one last coasting scenario. Now in this case, the rocket not only has a vertical velocity, but it's going to have a horizontal velocity towards the right. Now as the rocket enters the wind layer, it begins to pitch into the wind just like before. Now what happens though, is the wind pushing on the rocket increases the drag acting on the rocket. And that ultimately slows the rocket down. So it's not going to fly as far downrange due to the decrease in horizontal velocity. Now, at some point, the wind could be strong enough to ultimately push the rocket backwards. So the rocket will drift with the wind and maybe head back towards the launch pad. But as the rocket passes apogee, it'll begin to fall towards the ground, but it will have a horizontal velocity in the direction of the wind. So, when you're launching model rockets, you need to make sure you have an idea of what the wind is doing. You need to know the wind direction and the wind velocity. This will allow you to point your rocket in the proper direction to make sure it impacts downrange and well away from any spectators or the launch crew. Keep in mind that the magnitude of the effects of the wind will depend on a lot of things, such as the magnitude of the velocity vector and the magnitude of the wind blowing on the rocket. So in some cases, the effects might be small, but in other cases, the effects might be large. Well, that'll do it for this episode. Hopefully you have a better appreciation for how the wind affects the trajectory of a model rocket. Now visit LabRatScientific.com to learn more about spaceflight and rockets. Well, I hope to see you next time at LabRat Scientific.